such as implantable medical devices or military and space applications. The Chinese startup Betavolt claimed in January 2024 to have a miniature device in the pilot testing stage. It is allegedly generating 100 microwatts of power and a voltage of 3 volts, and has a lifetime of 50 years without any need for charging or maintenance. Betavolt claims it to be the first such miniaturized device ever developed. It gains its energy from the isotope nickel-63, held in a module the size of a very small coin. As it's consumed, the nickel-63 decays into stable, non-radioactive isotopes of copper, which pose no environmental threat. It contains a thin wafer of nickel-63 providing beta particle electrons sandwiched between 2 thin crystallographic diamond semiconductor layers. Gammavoltaic conversion. Gammavoltaic devices use a semiconductor junction to produce electrical energy from energetic gamma particles, high-energy photons. They have only been considered in the 2010s, but were proposed as early as 1981. A gammavoltaic effect has been reported in perovskite solar cells. Another patented design involves scattering of the gamma particle until its energy has decreased enough to be absorbed in a conventional photovoltaic cell. Gammavoltaic designs using diamond and Schottky diodes are also being investigated. Radiophotovoltaic, optoelectric conversion. In a radiophotovoltaic, RPV device, the energy conversion is indirect. The emitted particles are first converted into light using a radioluminescent material, a scintillator or phosphor, and the light is then converted into electricity using a photovoltaic cell. Depending on the type of particle targeted, the conversion type can be more precisely specified as alpha photovoltaic, APVV, beta photovoltaic, BPV or BEAT-PV, or gamma photovoltaic, GPV or GOM-PV. Radiophotovoltaic conversion can be combined with radiovoltaic conversion to increase the conversion efficiency. Pacemakers Medtronic and Alcatel developed a plutonium-powered pacemaker, the NUMEC NU5, powered by a 2.5 Ci slug of plutonium-238, first implanted in a human patient in 1970. The 139 NUMEC NU5 nuclear pacemakers implanted in the 1970s are expected to never need replacing, an advantage over non-nuclear pacemakers, which require surgical replacement of their batteries every 5 to 10 years. The plutonium batteries are expected to produce enough power to drive the circuit for longer than the 88-year half-life of the plutonium-238. The last of these units was implanted in 1988 as lithium-powered pacemakers, which had an expected lifespan of 10 or more years without the disadvantages of radiation concerns and regulatory hurdles, made these units obsolete. Beta-voltaic batteries are also being considered as long-lasting power sources for lead-free pacemakers. Radioisotopes used atomic batteries use radioisotopes that produce low-energy beta particles or sometimes alpha particles of varying energies. Low-energy beta particles are needed to prevent the production of high-energy penetrating bremsstrahlung radiation that would require heavy shielding.